Hello and welcome to another lecture of analog integrated circuit design. Just to summarize the previous lecture, we have analyzed the negative feedback amplifier with delay and we have determined the kind of solution that it is going to give. So, we have seen that if you have a delay in the negative feedback loop, it can be modeled using a delay Td in the feedback path, and this gives a differential equation which is that the derivative is the same as the delayed function, that is the derivative has the same shape as the delayed function, and the particular solution for a given input can be obtained by substituting the right boundary conditions as we saw yesterday. To obtain the solution to this, we assume that V naught of t is of the form of V p exponential sigma t, and while solving this we get the nonlinear equation which is sigma prime exponential of minus sigma prime tau equals 0, where sigma prime is the normalized sigma normalized to omega u by k, and tau is the normalized delay Td normalized to the time constant k by omega u, and we find that this has two solutions for tau less than 1 by e. Okay. So, we can list the solutions for different values of tau. For tau equal to 0, that is no delay, we have just a single solution and the other solution can be thought of as being at minus infinity. Okay. So, this minus 1 corresponds to a sigma value of minus omega u by k, and we already know that without delay, that is the solution. You get solutions of the form exponential minus omega u by k times t, and for t equals 0.1 you get something like minus 1.1 and minus 35.8 and so on. What happens is this sigma 1 goes on increasing, that is it goes more and more negative to higher frequencies. That means that the exponential corresponding to sigma 1 becomes faster and faster, and the exponential corresponding to sigma 2 becomes slower and slower, and for tau equals 1 by e, sigma 1 will be e and sigma 2 will be e. Here the sigma 1 and sigma 2 are the normalized quantities. So, when tau equals 1 by e, that is when the delay is approximately 0.36 of the time constant k by omega u, we get two identical roots which are at e times omega u by k, or that is the value of sigma, and or 2.718 times omega u by k. And as we saw yesterday, the interesting part is that with this much delay the response actually gets faster. There is no overshoot with this kind of delay. We have to see for larger values of delay what happens, because this particular equation has solutions only for tau less than 1 by e. So, just to remind you of the solution again, this is what we get without delay, and these four are the solutions with successively increasing delay. they are faster and there is no overshoot. In fact, it turns out that this one, the uppermost curve which corresponds to tau equals 1 by E, this is the fastest response you can get without overshoot. So, that is a good number to remember. So, to summarize, a little bit of delay actually helps, but too much of delay can harm, because we can easily see that there is a possibility of overshoot, and the best thing to have is tau equals 1 by E, because that is the fastest response you can get without overshooting in the step response. Overshoot refers to going beyond the target, which is unity here, and then coming back down and settling down slowly. Okay. Now, we will examine what happens when tau is greater than 1 by E. The differential equation, of course, is still the same. Now, the only thing is, earlier we assumed a solution of the form exponential of sigma t with a real coefficient in the exponent. That is what has to be relaxed now. We know that with a real coefficient in the exponent, we do not have solutions for tau greater than 1 by E. So, we have to have a complex coefficient okay, and with this we can substitute into the differential equation. dV naught by dt will be sigma plus j omega exponential sigma plus j omega times t, and that is equal to minus omega u by k, and V naught of t minus t d gives rise to a product of two exponentials, one of which is simply exponential of sigma plus j omega times t, and the other one is exponential of minus sigma plus j omega times t d. Okay. As before, this cancels out and we will be left with sigma plus j omega equals minus omega u by k exponential minus sigma plus j omega times t d, which can be written as minus omega u by k exponential minus sigma t d corresponding to the real part of the exponent, and exponential minus j omega t d, which can be further expanded into its real and imaginary parts. Okay. Now, we have two variables sigma and omega, and we need two equations to solve them. And if you look at this equation, we have the real part and the imaginary part on the right and left hand sides, and we equate the two to get the two equations. So, this is the real part and this has to be equal to this times cos, and this is the imaginary part and that has to be equal to this times sine. Okay. So, the two equations are and omega equals omega u by k exponential minus sigma TD sin omega TD. So, from these two we solve for sigma and omega. Okay. Let me rewrite the equations here. Okay. As usual, we do our sanity check. For TD equal to 0, the only satisfactory solution is to have sigma equals minus omega u by k and omega equal to 0. Okay. That corresponds to the case without delay. Now, again I will normalize the terms, so that we will end up with dimensionless quantities. I will define sigma prime to be sigma normalized to omega u by k. Similarly, omega prime is omega normalized to omega u by k, and tau is TD normalized to k by omega u. Okay. With this normalization, we can rewrite this as sigma prime is minus exponential minus sigma prime tau cos omega prime tau, and omega prime is exponential minus sigma prime tau sin omega prime tau. Okay. So, now we have a set of nonlinear equations. Before we had a single nonlinear equation, and even that could not be solved explicitly for sigma prime, but now we have two nonlinear equations, simultaneous equations, which have to be solved to get sigma prime and omega prime. Clearly, this is not possible explicitly. We cannot write sigma prime equals to this and omega prime equals to that, but we can try to get a feel for the nature of the solution. Okay. Also, one of the most important things is, when we were qualitatively discussing the effect of delay, we said it is possible that we overshoot and then undershoot and then we overshoot and then undershoot and never actually settle. Now, that will happen when sigma is positive, okay, because the solution is of the form exponential sigma plus j omega times t, and if sigma is positive, then this keeps growing, and if sigma is negative, it keeps falling. So, we have to find out at what value of delay the sigma becomes positive, okay, but we know that for a very large value of delay it is going to happen, because for a very large value of delay it means that there is no feedback for a long time and we keep going past the target by a large amount. Okay. So, we have to find out exactly what value of delay will cause this to happen, and that is why we need to get an idea of how the solutions to this equation look like. Now, to get a feel for the solutions, we can transform it into another form. Essentially, what we have to do is plot both of these equations on the same set of axes, sigma versus omega or omega versus sigma, and then find the solution. But these particular equations are rather more difficult to visualize. So, instead of these, we can transform them into two other equations. First, what I will do is I will take the square of the first and the second equation. This gives me because cos square plus sin square becomes 1, I get sigma prime square plus omega prime square is exponential of minus 2 sigma prime tau, and the next equation is obtained by taking the ratio of the two, which gives me sigma prime by omega prime is minus cos omega prime tau by sin omega prime tau. Okay. 3 and 4 are easier to visualize, and from this we will try to visualize the solution. And especially we are interested in the value of tau at which the system becomes unstable, that is sigma becomes positive. Okay. Now, in general, a set of equations like this for a particular value of tau will be solved numerically, and you can substitute the numerical value and find the solution after applying the boundary conditions. So, the first equation is sigma prime plus omega prime square equals exponential of minus 2 sigma prime tau. How does this equation look like when we plot it on a omega versus sigma plane? To see this, we can first consider the very familiar equation sigma prime square plus omega prime square is 1, which is the equation of a circle. Okay. A circle is something whose x coordinate and y coordinate when squared and add up to unity. Okay. Now, in this case, in our actual equation, right hand side is exponential of minus 2 sigma prime tau, okay, and not 1. So, what it means is the solution to this is some kind of a distorted circle whose radius goes on changing with sigma prime. Okay. And to get a feel for this, I will plot exponential of minus 2 sigma prime tau for some arbitrary value of tau. Okay. So, what the first equation is saying is that sum of sigma prime square and omega prime square is equal to this value, that is equal to this curve which is becoming larger for negative values of sigma prime and becoming smaller for positive values of sigma prime. So, compared to the circle, the new solution will look like this. It on the omega prime axis, it passes through unity plus and minus 1, and then on the right side you can think of it as a constantly reducing radius, okay, and on the left side the radius is increasing. Okay. So, this is what the curve will look like. This is for a particular value of tau, and if you increase the value of tau, you will find that it may not even form a closed loop, it may go off to infinity, because the exponential for negative values of sigma prime becomes very large. Okay. So, in fact, it may look something like this. Okay. And it turns out that for tau greater than 1 by e, this is exactly what happens. It will not form a closed loop. It is closed on the right side, passes through plus 1 and minus 1, and then diverges to infinity on the left side. Okay. We do not have to worry about the exact shape of this. This much detail is enough to get an idea of what the solutions are and when the system becomes completely unstable. Okay. And it passes through 0 1 and 0 minus 1. Okay. This is true for all the curves. So, this gives us an idea of what one of the equations look like. What we need to do is to plot the other equation and superimpose it on this graph and see what the simultaneous solution looks like. Okay. Let us now consider the second equation. This says that sigma prime by omega prime is minus cos omega prime tau by sin omega prime tau, and previously we plotted sigma prime on the x axis and omega prime on the y axis. Now, because here sigma prime appears only in one place, it is easier to plot omega prime on the x axis, and we can then turn the graph around and superimpose it on the other plot. I will rearrange it like this: sigma prime as a function of omega, okay, and this can be further rewritten as I have taken a factor of tau out of the equation, and if you look at this, we have sin omega prime tau divided by omega prime tau, which is a sinc function. Okay. So, that is what it is. It makes it easier to find out the value at omega prime equal to 0, etc. So, again I am going to plot this on the omega prime as the x axis and sigma prime as the y axis. Okay. So, first of all, for omega prime equals 0, the cosine is 1 and the sinc is 1. So, the result will be just 1 by tau. Now, before I plot the whole curve, I will plot cos and the sinc individually. And we know that both the cos and sinc are symmetric about the y axis, and so on. So, first I will plot the cos. It starts at unity, goes to 0 at plus minus pi by 2 tau, becomes minus 1 at plus minus pi tau, and does something like this. Okay. And I will plot the sinc separately. It starts from unity, and this becomes 0 at plus minus pi tau, and then it goes to a negative value, but not quite the same magnitude at 3 pi by tau, and then becomes 0 again at 2 pi by tau. Okay. This should be 2 pi by tau here, and the function is a ratio of these two. If I plot the ratio of this excluding the factor of 1 by tau, I will get something more than the cos, and it goes to 0 here, and here it goes off to minus infinity. Okay. And again at pi by tau it goes off to minus infinity. And if you look at the next segment between pi by tau and 3 pi by 2 tau, or minus pi by tau and minus 3 pi by 2 tau. The result is again positive. So, there is a discontinuity here. And then it also goes off to infinity at 2 pi by tau. In general, it goes off to infinity at every integer multiple of pi by tau. It could be plus infinity or minus infinity, and this is what it looks like. Okay. Now, the red curve is the plot of cos omega prime tau divided by sinc omega prime tau by pi. Now, as I have mentioned before, it is not sufficient to just watch me do this. It is much better if you try to solve this by yourself and plot it either using a numerical package or by hand by looking at the nature of the functions. So, then we will get a much better grasp of what the function behaves like. And I can't draw it here because of lack of space. This keeps repeating in every segment from 2 pi by tau to 5 pi by 2 tau and the next one and next one. The function jumps to plus infinity, then goes through 0 and minus infinity and so on. So, this keeps repeating. Okay. So, now this function has to be multiplied by minus 1 by tau to get what we want, to get the value of sigma prime. So, let me not put sigma prime here because that is not what I have plotted. I will do that in a new plot. Okay. If I plot it on a sigma prime versus omega prime axis, the value of this factor at omega prime equal to 0 is unity. So, our function starts from minus 1 by tau and it goes through 0 at these values pi by 2 tau, and then it jumps from plus infinity to minus infinity and does something like this. Okay. And so on. So, there are discontinuities at minus pi by tau, minus 2 pi by tau, plus pi by tau, plus 2 pi by tau, and in general every integer multiple of pi by tau. Okay. So, this is the nature of the solution. Sigma prime plus sigma prime versus omega prime looks like a cup in the middle and a lot of other segments with the discontinuities between them. Okay. Now, what we have to do is to overlap this with the other plot, which is the blue curve here, and we have to rotate the axis because this is plotted omega prime versus sigma prime and the other one is plotted sigma prime versus omega prime. So, we have to turn the plot around and then plot it. So, let us do that and see what the solutions do look like. So, the first equation is sigma prime plus omega prime, sigma prime square plus omega prime square is exponential minus 2 sigma prime tau. And I have already plotted this omega prime versus sigma prime, and the solution looks something like this. Let me mark unity here, plus 1 and minus 1, and as I said earlier, the solution will be an open curve, something like that. Okay. And the other equation, sigma prime by the other equation, sigma prime is minus 1 by tau cos omega prime tau by sinc omega prime tau by pi. This has a value of minus 1 by tau for omega prime equal to 0, and then it goes off like that, and it intersects the y axis at pi by 2 tau and minus pi by 2 tau. And then there are a number of other segments because of the discontinuity, something like this. Okay. There are a number of other segments like that. So, there are an infinite number of segments and therefore, an infinite number of intersection points. So, this means that in this particular case, we have an infinite number of values of sigma prime and omega prime, but except for the first pair here and here, all the other values are at higher frequencies, that is, the value of sigma prime is higher and the value of omega prime is higher, and because the value of sigma prime is higher in magnitude, those exponentials die off quickly and the solution is dominated by this one. The others do matter, they matter less than the first set of solutions. Okay. And also you see that the way I have drawn the plot, all the intersection happens in the left half side of this plane, that is for sigma prime values which are negative. So, this means that all the exponentials decay out and the system will be stable, but this is not unconditionally true. We can plot it for a different value of tau and see what happens. So, you observe that for a smaller value of tau, this point minus 1 by tau will be further to the left, and this point pi by 2 tau will be further up on the y axis and further down on the y axis here. So, that means that the points of intersection will be further negative. Conversely, for a large value of tau, this end of this cup moves inwards, it moves to the right, and also these points of intersection move in, okay, they move closer to the origin. Okay. So, for a larger value of tau, I will plot it here. The point of intersection may be in the right half plane. Okay. For a larger value of tau, the blue curve also changes to this green curve, but it always passes through plus 1 and minus 1. Okay. So, there is a certain value of tau beyond which the intersection happens on the right side of the curve for sigma prime greater than 0, and we know that for sigma prime greater than 0, the solution does not decay to 0, but it blows up exponentially. So, which means that the system is unstable. Now, it does not matter if you have a number of intersection points with sigma prime less than 0. What matters is, even if you have a single pair of points with sigma prime greater than 0, the solution will blow up and the amplifier is not usable. What is meant by blowing up is that when you do not have an input because of some initial condition, the output simply diverges. We expect that the amplifier will respond only to its input, it will give you k times the input voltage after reaching steady state, but if the amplifier is unstable, it is not going to do that. Even without an input, it is going to give its own output, and the output is going to be unrelated to the input, and it will soon become very large. Okay. So, the amplifier becomes unusable if the poles are in the right half plane. Now, we have to find out the value of tau for which the solution moves to the right, and this is rather simple because the solution to the first equation, the plot of the first equation always passes through plus 1 and minus 1 on the omega prime axis, and the plot of the second equation passes through pi by 2 tau and minus pi by 2 tau. For the intersection to happen in the right half plane, this cup has to be within the plus 1 and minus 1. That is to say, this point of intersection pi by 2 tau has to be less than 1. Okay. So, we will get instability, which means some value of sigma prime more than 0 for pi by 2 tau less than 1. In other words, tau greater than pi by 2. Okay. So, that is what we have learned by plotting these two nonlinear equations on a single pair of axes and finding out the points of intersection. To summarize, for tau greater than 1 by e, for which we could not find the points of intersection from the earlier method, we had to admit a complex solution sigma prime plus j omega prime. First of all, there are an infinite number of solutions. Okay. You have sigma 1 prime, sigma 2 prime and so on, the list never ends, and similarly omega 1 prime, omega 2 prime and so on, and the list never ends. So, if you have an infinite number of solutions, what is the final form of V naught as a function of time? It will be sum of all possible I have to run the summation from 1, sum of all possible exponential solutions. Okay. So, this is what we have to do, and from the boundary conditions we can try to determine a k, but of course, it is not possible to take all the infinite terms. But what happens is that there is a pair of solutions here and here which are closer to the origin, and all the others are much further out. So, you can take only this and get a reasonable approximation to the solution, or maybe you can take this and the next one and get a reasonable approximation and so on. You do not have to take all the infinite number of terms. If you want to write down the solution, you approximate this by a1 exponential sigma 1 prime, sorry, I have to make this sigma 1, not sigma 1 prime, sigma 1 plus j omega 1 times t, okay, where sigma 1 and omega 1 are the lowest frequency solutions. That is the ones that are closest to the origin. Okay. So, this is what happens, you get an infinite number of possibilities for sigma and omega, but you take the lowest frequency ones and you will get a reasonable approximation to the final solution. So, another important thing that we notice is that there is at least one value of sigma prime which is more than 0, which means one value of sigma which is more than 0 for tau greater than pi by 2, which means that the delay Td is greater than pi by 2 times k by omega u, okay, and pi by 2 we know is approximately 1.5 k by omega u. We have all along been saying that if you have a delay that is very large, the system will become unstable. Now, we know exactly how large that is. If you have 1.5 times the time constant, the system will become unstable. If you have a delay that is 1.5 times the time constant, the system will be unstable. Okay. So, you have to keep the delay to be much smaller than 1.5 k by omega u. Okay. And what do the solutions actually look like? Because earlier for tau less than 1 by e, we saw that the output voltage V naught started from 0 and then reached the output without overshooting. Now, in this case we have said that we have admitted exponential solutions. In this case we have said that we have admitted complex coefficients inside the exponent. What it means is solutions of the form exponential sigma 1 plus j omega 1 t accompanying this you will always have exponential sigma 1 minus j omega 1 t, because you see that you will always have a symmetrical pair. If you have a point of intersection here about on its mirror image about the x axis, you will also have a solution, and this can be written as exponential sigma 1 t and 2 cosine omega 1 t. Now, if you have different coefficients here and there, let us say a1 and a2, you will be able to write it as a1 exponential sigma 1 t cos omega 1 t and some other a2 exponential sigma 1 t sin omega 1 t. So, the solutions will be in terms of sinusoids, cosine or sine, which is modulated by an exponential, and if the value of sigma is negative, the exponential dies out and the sinusoid also dies out, and if the value of sigma 1 is positive, the exponential blows up. But we will not be very interested in looking at positive values of the exponential, because that simply says that the amplifier is not usable. What we want to find out is the delay for which that happens and make sure that we never get there. Okay. We have to find reasonable values of delay for which you have sinusoids that are decaying and the amplifier is still usable. Okay. And let us look at some example solutions. So, here is what happens. Again, for reference I have shown the case without delay, and this plot is obtained in a way similar to the last one, that the input goes from 0 to 1 by k and the x axis is normalized to k by omega u. 2.5 means 2.5 k by omega u and so on. Okay. So, no delay case of course is the exponential, and I have shown it also for a small value of delay, that is tau equals 0.1, and you see that is quite close to the case with no delay. This is what we knew all along, and then this is the one for which tau is 1 by e. Okay. This we said is the fastest response we could get without overshooting, and any tau that is larger than this results in an overshoot, as exemplified by the green curve. Okay. So, this is for tau equals 0.7, the output goes up and then comes down below 1 and then settles. This is not going back and forth too many times, so this may still be acceptable, but if you look at the next case, this one for which tau is 1.3, then you can see that it is going up and then coming down and going up and coming down, and at 10 time constants the output is nowhere near settled, it will go up and down many times. Okay. And finally, we have the pale blue one which corresponds to tau equals 1.5. Okay. This is just smaller than pi by 2. For pi by 2 we know that it becomes unstable. This is stable, because you see that the amplitude of the ringing is decreasing. Here it is 2 about 2 and here it is smaller, and it will become smaller, but it will really take a long time to settle. So, you do not want any of these things, you would not want to use this much delay. So, this is about the maximum that you can tolerate, or in practice maybe even smaller, about tau equals 0.5 or so. Okay. For that there will be just a little bit of ringing and not much overshoot, and the response dies out in a reasonable time, and you will get the steady state solution in a reasonable time. Okay. Now, let us look at another plot to appreciate this instability better. Okay. So, in this case what I have done is to calculate the output V naught of t by numerically solving all the equations that I had put up earlier, and for 3 cases I have done it for tau equals pi by 2 and tau equals 1.5, which is a slightly smaller delay than pi by 2, and tau equals 1.6, which is a slightly higher delay than pi by 2. The pale yellow curve whose amplitude is decreasing is the solution for tau equals 1.5. We can see that it is stable, that is, the sinusoidal ringing does die out after t equal to 100 time constants. It has still not completely died out, but if you wait for 1000 time constants it will die out. Now, this is a stable system technically, but this is not a usable amplifier though, because it takes a really long time to settle, because you can compare it to the case without delay, and that is settling within a few time constants, whereas for tau equals 1.5 it has not settled even after 100 time constants, but technically it is stable, because if you do leave it for long enough it will settle to the steady state. Okay. Now, the red one, the red curve here is the case for which tau is pi by 2. Okay. And you can see that it produces a sinusoid of constant amplitude, and this makes sense because for tau equals pi by 2 the points of intersection will be exactly on the y axis. So, that means that sigma prime will be 0, the exponential will simply become unity, and the omega prime will be corresponding to these 2 points plus or minus 1. Okay. So, you get a sinusoid with a constant amplitude without any damping. Okay. For tau equals pi by 2 you get sigma prime to be 0 and omega prime to be plus or minus 1. Okay. And that corresponds to the constant amplitude sinusoid, or the poles being exactly on the imaginary axis or the y axis. And if you now go to the other case where tau is slightly greater than what is required to have the poles in the right half plane. So, you will see that sigma is positive. So, the amplitude of this sinusoid goes on increasing. Okay. So, in this case sigma prime is positive. So, the solution blows up, and if you wait for long enough it will blow up to infinity. Okay. So, this is the general nature of the solution. You always want to be sufficiently below tau equals 1.5, probably close to tau being 1 by e, where you get the fastest response without overshoot, or approximately tau of half, which gives you very little overshoot. Okay. And this tau equals 1.5 or tau equals pi by 2 puts an absolute limit. After this the amplifier becomes unusable, because you will get an exponentially increasing sinusoid, and soon because of nonlinearities in the system the system becomes an oscillator with a constant amplitude. This is what you want to do if you want an oscillator, not if you want an amplifier. Okay. Finally, a quick summary of negative feedback amplifier with delay. The small delays actually help you, they speed up the response, and this is because with a small amount of delay you are always accelerating a little more than you should. For tau equals 1 by E, that is Td is about 2.7 times the time constant k by omega u, you get the fastest response without overshoot, and for tau between 1 by E and pi by 2, you get a stable response, but with ringing, and for tau greater than pi by 2, the system is unstable. And in practice, you would limit tau to about 0.5 or less, so that even if there is a ringing, it is very small in magnitude and it dies out very quickly. Okay. So, that is a summary of what happens to a negative feedback amplifier in presence of delay. So, that should give you an idea of what kind of delays are tolerable, and how this affects you in practice is that when you try to implement the amplifier, the technology with which you implement imposes a certain lower limit on the delay. So, this means that your time constants and the speed of the amplifier will be limited. Okay. See you in the next class.